Welcome to my video on gravitational potential energy. Earlier we had talked about potential energy, which is essentially a stored energy, which is stored within different types of forms. You could have elastic potential energy, or you could have, say, gravitational potential energy. In this video, I'm going to be talking about gravitational potential energy. So let's start off with the definition of gravitational potential energy. Gravitational potential energy is a stored energy. I'll just highlight stored here, that has to do with or associated with the position of the object that is within some gravitational field. All right, let's take a look at the picture over here to the right side. Suppose you have an object, in this case this rock over here, and it is being lifted upwards some vertical height, which is represented with delta y. And it's being lifted within some gravitational field. The gravitational field is uniform. Let me draw it for you. These evenly spaced red arrows pointing downwards represent the gravitational field. The strength of that field is approximately 9.8 newtons per kilogram. And since they're all evenly spaced and all pointing downwards, this is what we call a uniform field. So for our system, let's include the object right here plus the Earth. So this circle represents my system, and inside my system is the rock and the Earth. And because we consider both the object and the Earth being our system, then we are really, in effect, including our gravitational field, which is represented by these red arrows. So let's suppose you were to lift this object with your hand. There's my hand. And you would be applying an external force, which I'll label with this blue arrow, upwards. And as you apply this force upwards, you would be doing positive work on the system. Remember, your force would be up and your displacement would be up. This causes the energy of our system to increase. And that increase in energy, or that gain in energy, is known as gravitational potential energy. Maybe this analogy will help you. Think money. When work is done on an object and you're lifting it vertically up, it's similar to the idea that I go to work every day at school. And eventually at the end of the month, I get a paycheck and money is deposited into my bank account by my employer. The money that is in my bank account is a stored money, I guess. And so you could kind of make the analogy that it's like gravitational potential energy. And me showing up to school every day and teaching is like, well, I'm coming to work, and hence I'm doing work. And so in the end, the work that I do is equal to the money I get at the end of the month, hence the work energy theorem. Now, how do we calculate the amount of work that is done in lifting this object upwards, this vertical displacement delta y? All right, just erase these red lines just because it clutters my image. So let's suppose that I'm moving this rock upwards at a constant velocity. Hence, when I get to the final position, I'm still applying that force upwards. And when you look at this object, there's two forces acting on it. There's the external force provided by my hand on the rock, and then we have the force of gravity acting downwards, mg. And since I'm moving upwards at constant velocity, there's no acceleration, and so this force and this force must be equal to each other. Now you might be wondering, why am I doing this at constant velocity? Well, that's because I don't want the object to speed up or slow down. I don't want it to be changing kinetic energy. See, if it was speeding up, then I have to deal with a change in kinetic energy as well. I really want only one energy to increase, and that's the gravitational potential energy. So as I apply this external force F, I'm causing the object to move up this displacement delta y, or you could call it d. So the displacement d is really equal to delta y, And as I mentioned earlier, my external force must be equal to my force of gravity. So F external must be equal to Fg. To calculate the work done, we use the formula W equals F parallel times D. And in this particular case, the parallel force is exactly in the same direction that I'm moving. So F parallel is really equal to my external force, which is also equal to my force of gravity. So then I could replace the parallel force with Fg, and I could replace my displacement with delta y. And of course, the force of gravity is also calculated by using m times g. So then my work done by my hand would be equal to m times g times delta y. This work done is equal to the change in energy of the system. And that change is equal to gravitational potential energy. So really that work done is equal to the change in stored energy from the gravitational field, within the gravitational field. So delta U sub G is really the change in gravitational potential energy. And this equation is written like this on the AP formula sheet. You can see that the gravitational potential energy is directly proportional to the height. So of course, if you lift it up higher, you're going to have a bigger change in gravitational energy. And it's also proportional to the mass. If you were lifting a heavier object, then you'll have a greater change in gravitational potential energy. And lastly, it depends on the gravitational field. Gravitational field on Earth is 9.8, but in other places like the moon, which is about 1/6 of what it is on Earth, then you're not going to have as large of a gravitational change in energy in that case. So it does depend on the gravitational field strength as well. Most of the problems that you'll be using this formula will be on the Earth. So G is basically equal to 9.8 newtons per kilogram. Now, let's suppose once the object gets to the very top of its path, at that position, let's define that. Let's call that position y sub 2. All right? And let's say we allow this object to simply fall freely under the influence of gravity. As the object falls, it'll continue to gain speed and hence gain kinetic energy. So within our system, what we find is that the gravitational potential energy is now being transferred or transformed into kinetic energy. If the object is dropped in a completely frictionless system with no air resistance, then the gain of the kinetic energy would be exactly equal to the loss of gravitational potential energy. A good simulation demonstrating the conservation of mechanical energy and using kinetic and gravitational energies is this energy skate park simulation from the PhET website. Suppose the skateboarder starts from rest at the top of the hill. As I release the skateboarder from the top of the hill here, you'll see the green will start to increase as it goes down. The green part here represents the kinetic energy. The blue part of the pie chart represents the gravitational potential energy. So as the skateboarder goes down the hill, you have increasing kinetic energy. And as you go back up the hill, you have increasing gravitational energy. And they're continuously being transferred from one form into another form. Now I'll just show you what it would look like in terms of a bar graph. I'll press play here, and you can see how the kinetic energy and the potential energy is changing over time. You see, the green one here represents the kinetic energy curve, which is increasing like a parabola, and the blue one over here shows the potential energy decreasing and then increasing like a parabola as well. And then the solid line up here represents the total amount of energy. The sum of the thermal energy, the potential energy, and the kinetic energy will all add up to the total energy, which remains constant within our system. Okay, back to our notes. When problem solving, it is helpful to choose an appropriate reference level where the gravitational potential energy is equal to 0. You see, I started off with this y2 over here, and then I've labeled over here the final position y sub 1. You could define the gravitational potential energy by simply just using this formula UG equals mgh. Or in retrospect, actually, we now use the variable y in the notes now. So the potential energy at this particular location, we'll call it UG sub 2, would be mgy sub 2. And the potential energy at this final position would be UG, say 1, equals mgy sub 1. And then the change in gravitational potential energy would be mgy2 minus mgy1, which then in the end gets you just basically mgy2 minus y1, but y2 minus 1, y1 is really just delta y. So this mg delta y represents the change in gravitational potential energy and is also the work done. In this setup, I've decided to choose to have my reference point be the ground level. Therefore, both position initially and finally will both have gravitational potential energies. You could decide to choose your reference level wherever you want. I mean, you could have, say, a table over here and decide that this is your initial y being 0. And that's totally fine. It's really up to you. You could even have the initial position up here, have that be y equals 0. Because in the end, all you really care about is the change in height, or delta y. You don't really care about the initial and final positions, just the difference between those positions. However, personally, I find it the most convenient to choose the lowest point to be 0. In fact, I would actually decide that this position right here, this y1, I would set that to be equal to 0, and then y2 would be just really delta y. So it's really up to you which place you want to call your reference level to be 0. Again, I choose this point to be 0 often because then anything above it will be a positive gravitational potential energy. And then nothing lower than that, because there's not going to be anything lower than that, then that's fine because I won't have any negative changes of potential energy. I personally like to think of my bar charts all having positive energy. It just makes it a little bit easier to solve. So that's my suggestion, but it's really up to you. All you really have to care about is just that delta y in the end. One last thing. Since the force of gravity is what we call a conservative force, the gravitational potential energy change, say from this particular location to this particular location, really only depends on the vertical displacement, delta y. That means that if you had a hiker that would travel path A along here, and then another hiker that takes path B along there, both hikers would experience the same change in gravitational potential energy. Hence, basically, it's path independent. It really doesn't matter what path that you take. All you care about is where you start and where you end, because the change in gravitational potential energy is really only going to depend on the mass, the gravitational field, and the vertical displacement. Okay, and that's it for this video, and I think you can now start doing some problem solving with potential energy.